Welcome to today's explainer. Beneath every single text you send, stream you watch, or call you make, there's actually an invisible structural battle happening inside our computer networks every single day. A really complex decision is being made behind the scenes about exactly how your data is going to travel. So today, we're going to break down the two reigning champions of network communication, getting right to the core of how our digital world actually functions. So here's the core question we're answering today. How do these networks actually establish connections to move all of our data? We kind of just expect our information to instantly appear, right? But there are actually two vastly different architectures that our digital world uses to get information from point A to point B. It's a truly fascinating structural difference, and honestly, understanding it completely changes how you see the internet and telecommunications. Here's a quick look at our agenda. We'll start with establishing the connection, then we'll get into circuit switching explained, followed by packet switching explained. After that, we'll do a head-to-head comparing the two methods, and finally wrap up with use cases and a summary.
Okay, Section 1, Establishing the Connection, the Need for Switching.
Moving right along to Section 2, Circuit Switching Explained, the traditional heavyweight.
Let's start with circuit switching. This is a method where a dedicated physical connection is established between a sender and a receiver for the entire duration of a communication session. I want you to think of it like a continuous, unbroken pipe that is held open just for your data for literally as long as you need it. Let's look at exactly how this operates under the hood. First off, it operates right at the foundation, OSI layer 1, the physical layer. Because it establishes that actual physical connection, it features incredibly low latency once the setup is complete, which makes it highly efficient for continuous real-time communication. But here's the major catch. Resources are reserved and allocated for the entire duration of the connection. That means even if there's total silence on the line, like no data being transmitted at all, those network resources stay completely locked up. On the plus side, errors are pretty rare because the connection is dedicated and less prone to outside interference. But, if an issue does occur, it usually results in a completely dropped connection. Ultimately, it's just a bit less adaptable to the diverse mixed traffic we see today. The classic example here is the traditional landline telephone network. You pick up a landline, and a physical circuit is closed and held open, absolutely monopolizing those specific network resources until you finally hang up the receiver. All right, Section 3, Packet Switching Explained, the dynamic contender. Now, with packet switching, absolutely no dedicated connection is established. Instead, data is chopped up into tiny segments called packets, and each one is routed completely independently. So rather than that unbroken pipe we just talked about, imagine sending discrete little datagrams that independently scramble and navigate their way across shared network paths to eventually reach the exact same destination. Let's break down the technical specs of packet switching. It operates a bit higher up the stack at OSI layer 3, the network layer, relying on IP addresses to find its way around. It is highly efficient for bursty data traffic because resources are dynamically allocated based on demand. And because those individual packets are taking all sorts of different routes, they have variable transmission times. Actually, they might even arrive completely out of order, which means they require reassembly at the destination. Errors aren't handled at the physical layer like with circuit switching. Instead, they're corrected at higher layers, like the transport layer. All of this basically means packet switching is incredibly flexible and highly adaptable to different types of data traffic, everything from voice to video to super complex applications. The ultimate prime example of this, the internet and modern data networks. You're watching this explainer right now because bursts of data packets are traveling dynamically to you, sharing network capacity, and reassembling on your device in real time. It's pretty wild when you think about it. Okay, Section 4. Comparing the two methods, the showdown. Okay, let's dive into this comparison. When it comes to resource allocation, circuit switching essentially hoards network capacity. It requires reserved space whether you're actively speaking or just sitting there in total silence. Packet switching, conversely, democratically shares the network, allocating those resources dynamically, exactly on demand. Now, what's really interesting about this is how it introduces a distinct trade-off regarding delay. Circuit switching gives you guaranteed low latency, continuous flow. Packet switching, on the other hand, offers a completely different reality. Variable delay for bursty traffic, making delivery a lot less linear, but immensely efficient. So the absolutely crucial point here is how this translates to adaptability. Circuit switching operates on the bare metal physical layer 1. It does one thing, a continuous connection, very well, but it's just much less adaptable to mixed data types.
Packet switching operates based on IP addresses at layer 3. This makes it far more versatile, capable of effortlessly juggling the completely diverse multimedia applications that we rely on every single day.
And finally, Section 5, Use Cases and Summary, Choosing the Right Tool.
And this brilliantly illustrates that neither method is universally better than the other. It's really all about choosing the right tool for the job. If you have continuous, real-time needs where consistent flow is absolutely paramount, circuit switching is perfectly suited for that. But for bursty data where efficiency and sheer volume matter, packet switching is for sure the undisputed choice. As our source material perfectly sums it up, both switching methods have their strengths and are used in different contexts based on the nature of the communication and the requirements of the application. It just reinforces that network architecture is driven entirely by the specific needs of the traffic you're trying to handle. I'll leave you with this thought to ponder as we wrap up today's explainer. As our global data needs grow exponentially, are we going to rely almost entirely on the dynamic sharing of packet switching, or will new, incredibly advanced real-time applications demand a return to the guaranteed, dedicated physical connections of circuit switching? It's a fascinating question about the future evolution of network engineering. Thank you so much for joining me to explore this topic, and keep on learning.